Hey guys, thank you for tuning in to the continuation of this problem, part B, specifically finding the rate constant right after we found the rate law. So basically, we did all the hard work. We did all the really hard stuff, and now finding the rate constant has become fairly simple. It's just taking this information, taking our rate law, and plugging in any type of experiment that we want. Any experiment, 1 through 5, we can plug it in and we can find the rate constant. And in fact, I'll prove that you can plug in any experiment that you want and you'll still get the same rate constant. So let me erase this work and I'll rewrite what we got for part A if you did not get a chance to record it down. All right, so we said that our rate for this problem was equal to some constant that we need to find times iodide to the first power. We solved that x was 1 times peroxo disulfate to, once again, the first power. That's what y is equal to. And now we'll, test two experiments just to prove that our k value will be the same for no matter what experiment that we test. So let's try experiment 3 and experiment 5, two experiments that we really didn't touch so far. So experiment 3 we'll use, and we'll solve for that first, and I'll do it in red. So the rate we get for experiment 3 is 6.25 times 10 to the power of negative 6, which is equal to the molarity, which is equal to a constant, times the molarity of iodide, and specifically in experiment 3, the molarity of iodide was 0.080 to the first power, times the molarity of peroxo disulfate. Specifically in experiment 3, it's 0.020 to the first power because x is equal to 1 and y is equal to 1. So now we can divide both sides by 0.080 to the first power times 0.020 to the first power and divide it to this side to get k all by itself. All right, so I'm going to just denote two little quotation marks just so that it's the same thing we're dividing by. And we would get k is equal to 0.0039. 0.0039. Now, what units could k be? Well, let's think about it. We have something to the first power, a molarity to the first power, and the units for molarity is moles per liter. And we have another molarity to the first power, which is moles per liter. And of course, both of these things are times a k, which we don't know the units of. But we know that the rate is equal to moles per liter times second. So we need to find a unit for k that will allow all three of these things to be multiplied and get this unit, the moles per liter times second. Well, what do we have so far? We have that if we multiply moles per liters twice, we will get moles squared per liter squared. So how can we get moles squared per liter squared to moles over liters times seconds? Well, that's very simple. We have to do liters on top, and we have to do moles times seconds on the bottom. Well, why? If we see here, liters and 1 liter here will cancel out. Okay, so this will be liters to the first power. And 1 mole here and the moles here will cancel out. So this will be moles to the first power. And we have seconds at the bottom. So what are we left with? Well, we're left with moles per liter, because liter to the first power remains, times seconds. So we get the same units that we need to get. So in this case, the units for k will be equal to liters over moles times seconds. All right? Now I'll do my second proof. My second proof will confirm that you could use any experiment in our experimental data set and you'll still get the same k value. So in green, I'll try experiment 5, another experiment that we didn't touch. We know that experiment 5 has a rate of 7.00 times 10 to the power of negative 6, which is equal to some constant that we need to calculate. And the molarity of iodide is 0.060, 0.06 in experiment 5. so 0.060 to the first power because we solved for x in part A. And the molarity of peroxide disulfate is 0.030 to the first power because y is equal to 1. Now we'll divide both sides by 0.060. I'm sorry, that's kind of messy. Let me rewrite that. 0.060 to the first times 0.030 to the first. And we'll divide both sides by the same thing, so we can cancel these out. And we're left with k. Now if you type this into your calculator, you will get the same value, 0.0039 liters per moles times seconds.